Hi, welcome to 3.2 Exponential Decay connecting to negative exponents. Our success criteria. I can model situations with exponential decay. So in these next few videos for this lesson, we're going to look at real life applications where we use exponential decay to model what is happening. And then simplify and or evaluate expressions with negative exponents. So be able to apply exponent rules. Some of these rules you have already learned. Some of these will be new. We want to make sure we can use them accurately. And then lastly, make connections between negative exponents and exponential decay. So what is exponential decay? Well, it's just a pattern of decay in which each term in the pattern is multiplied by a constant fraction between 0 and 1 to produce the next term. So we can see that in here. If we had to multiply by something to get the next term, we can see we only need to multiply by a half each time. So every time we multiply by a half, we actually produce the next term. So we can see they're consistently getting smaller and smaller each term. So in terms of a graph, that's going to show up as a function that's constantly decreasing, and it'll actually be decreasing at a decreasing rate. And it has a repeating exponential pattern of finite differences. The ratio of successive finite differences is constant. So this is something that we will always see with exponential functions. When we perform the finite differences, we will see a common ratio amongst the differences. What that means is they will never reach a constant amount or converge to a constant number like linear functions or quadratic functions do. Okay, let's take a look at the graph for an exponential decay function. So I've set this up so it kind of animates the base. So here we have an exponential function, y equals b to the exponent x. So there's the equation. I called the base b because it kind of represents the base for the exponential function. And there's a slider for the base. So it just kind of, right now it's set to go between 0 and 3. So I can manually adjust this slider. So right now it's at 0.7. And as I make the base smaller, notice how the function decreases more quickly. So it gets steeper and steeper. As I increase b, the function actually starts to get flatter. So the smaller the base, the faster it decreases. If I go greater than 1, that means the factor which I'm multiplying is bigger than 1, and that would actually produce growth. So anything greater than 1 is exponential growth. We can see how the function going from left to right is increasing. The bigger the base is, the faster it increases. Okay, the only number that's not allowed here is 1. Okay, because if the base is 1, well, 1 raised to any exponent will always just equal 1. So 1's actually not allowed. We don't include any negative numbers for the base either. But so anyway, for just for exponential decay, our values are limited from 0 to 1, and then anything after 1 is considered growth. One other thing I want to point out on the graph is that this never touches the x-axis. Okay, there is a horizontal asymptote, so the function will continue getting closer and closer, but it never ever crosses. I provided the link for this in the PowerPoint, so feel free to open it up and then kind of investigate on your own. So back to the PowerPoint. So let's kind of compare growth and decay a bit, just to summarize a few things. So for growth, the base is greater than 1. For decay, it's between 0 and 1. So you can see here as the base increases on these functions, the function will actually grow more rapidly. For decay, as the base gets smaller, the functions decrease more quickly as well too. Okay, we say that the growth one increases over the domain because it's an exponential growth function, and this one decreases over domain because it's exponential decay. They both have y-intercepts at 1 because anything raised to the exponent 0 is just 1. And they both have a horizontal asymptote of y equals 0. This is because no matter what you put in for the exponent, you will never ever get 0. So this power can never equal 0. All right, let's talk a little bit about the finite differences. So both growth and decay cannot reach constant finite differences. This is because successive terms in the finite differences will have a constant ratio. What is the constant ratio for this example? So let's go ahead and take a look at that function right here. This is exponential decay because b is a half. So I'm going to go ahead and plug these values of x into the equation to calculate y. So a half raised to the exponent 0 is 1. Half to the 1 is a half. A half squared, I have to square the numerator and the denominator. So 1 squared is 1, 2 squared is 4. A half cubed, 1 cubed is 1, 2 cubed is 8. And then a half to the exponent 4. 1 to the 4 is 1, 2 to the 4 is 16. Our finite differences. Let's go ahead and start the first difference. So a half minus 1. We always do final minus initial. So a half minus 1, that's equal to negative a half. Then we have a quarter minus a half. So a quarter is smaller than a half. We're going to get a negative number. We get negative a half. Sorry, we get negative a quarter. Let's fix that real quickly. So we get negative a quarter. And then an eighth minus a quarter. That gives us negative an eighth. And then a 16th minus an eighth. That gives us negative 1/16. Okay, moving on to our second differences. So negative 1/4 minus negative a half. That means negative a quarter plus a half. That's going to give us a positive a quarter. Negative 1/8 minus negative 1/4. That means we have negative 1/8 plus 1/4. That's going to give us positive 1/8. And our last one, negative 1/16 minus negative 1/8. That's negative 1/16 plus an 8. That's going to give us positive 1/16. All right, so notice we're not reaching a constant value. I actually see a pattern here. I see that these values here just become negative over here. So they kind of repeat but become negative. And then the second difference is they become positive again. So I'm kind of seeing a repeating pattern. I also see a common ratio of multiplying by 1/2 to get the next term in the finite differences. So you can see that exists all the way across the board. So that will be true for all the finite differences for this function. And you might have also noticed that common ratio, so the common ratio is a half, it's also the base of the function. So that will always be true for exponential functions. And for decay functions, this ratio is always going to be smaller than 1. And you can see a half is, sorry, it's supposed to be between 0 and 1. So our common ratio is a half, that's between 0 and 1. That will always be true for exponential decay. All right, that's it for this video. In the next video, we'll talk about some applications for exponential decay. And then after that, we'll work into our exponent rules. Okay, I'll see you soon.